All right, let's fit some functions to data using this four parameter ABCD thing that we looked at already. I'm going to start with what looks to be basically a sine curve and see how we do. I have that data over here, so I have that data in a spreadsheet, and I want to put it into Desmos, and so I'm going to highlight only the data, not the labels at the top, and there's quite a bit of data. Okay, so what I have is 365 days worth of sunlight information. So as I go back up here, now I can copy and then I'll paste in Desmos. Now when I paste in Desmos, I can't use the mouse. I'll have to use Control V to paste. But as you see these are all numbers between 0 and 1. I got them from this original sunrise sunset data set here, and it has 2:53 p.m. to 9-10 a.m. for sunrise. I'm pretty sure, actually I haven't checked it, but I'm pretty sure what these decimals are the percentage of the 24-hour clock, but between sunrise and sunset. So you get down here in January 1st, it's about a quarter of the hours, so about 6 hours between sunrise and sunset in Anchorage, Alaska. And I looked, the biggest it gets is over 80%. And you'd have to go back to like December 21st to get the smallest. But we'll see that in a moment. And okay, so I've done a copy on the data. Now I'll go to Desmos, and I will simply click in here. It's already in there, and I'll do a Control V for paste, and there we go. And I have X1 and Y1, and there's my plot. Now we'll get to this some work over here in a minute where I messed with it a little bit differently. But what we want to do, right, is we want to take f of x equals, and let's go with sine. We could go with cosine, but I'll do sine of x here, and on this it really filled that in a lot because this goes clear over to 365, so the sine will definitely move up and down quite a bit. It goes up to 1, down to -1, and so forth. Now I'm going to call g of x equal to a times f of b, then in parentheses x minus c, and then plus d. And it wants to know, do I want to add sliders? And I'll do that. And it filled in all kinds of stuff here. And now what I want to do is turn off F and look at this. Now, the neat thing with something like Desmos and the sliders is I can just start playing with things. Now, B, for instance, A, I need to get the amplitude. So if I look at the vertical stuff, the two things for vertical are A and D, and so, well, A needs to be smaller. Now, what I can also do to make my life easier is probably, well, let me move my face here for a moment. We can probably move it up here over the data. doesn't really matter. Um, but so I'm looking down here, and I see this goes to what, 365 and so forth. Well, I can, oops, I'm not sure what just happened. I'm trying to move this, so I'll move it down, and I can use my mouse wheel and make this a little bigger so I can see. But I can go vertically with A and D here, and as I look at this, the sign is usually at 0, right? As far as up and down, it's centered at 0, and I can look here and see, oh, it looks to be maybe around 0.55 is the middle of this thing, and so I can do that. Oh, I need to. I kind of lost track as to what the heck was I doing when I moved my picture, and I was actually looking for something to increase the size of the type font here, but it's not there, so I had to use the Control Plus thing on the web page. Okay, so back to this. I know I want C somewhere around 0.5, 0.55, something like that, and so to use the slide bar better, I'm going to change this and say, well, I know C isn't going to be any smaller than like 0.3. Wait, why C? Quit that. I want it to be on D. It's no smaller than 0.3 and no bigger than maybe 0.7. Okay, so I do that, and it moved it to 0.7 because that's the biggest it could be. It had been at 1, and I can kind of move this down somewhere around where I think it should be. Now that's still a bad picture, but that's because the amplitude's too big, this A, and I know that the amplitude is going to be, if it's 1 times sine, it goes up as high as 1 and down as low as -1, and so I want the amplitude to be about half this distance, and I can just sort of eyeball it here and see, well, there's 0.2 to 0.8. That's again also about 0.5, and so here I know I don't want it any smaller than probably 0.2 and no bigger than 0.8, and so I do that, and I shrink it down somewhere around 0.5, and I look and I go, oh, well, actually that looks too big, all right, 0.5, and yeah, what is this, 0.8 to 0.2? That's, yeah, so it should be, that's 0.6, and so half of that's about 0.3. So I want to get this down, here. Now notice, so by sliding it, the top is right there, the bottom's right there. So 0.31 is a little too big. I'll get it here at 0.3, which is a little too small. But now I'll take D and slide it up a little bit. Well, I mean, it looked a little too small in some sense, and I see that, and it looks just slightly too big. Now we'll get into the philosophy of all this in a moment, but yeah, I'll leave it at 0.29 and leave the D at 0.51, and so up and down it looks like we've done pretty well. Well, now similarly, we need to mess with B and C, and B needs to be a big number because, again, making B bigger than 1 is going to stretch this thing out, so I can start doing the, oh, I said that backwards. I am sorry. B needs to be smaller than 1, and that's where you can, I misspeak, and immediately I went, oh wait, I didn't say that right. And, because I could see that I was just wrong. And I'll misspeak more than once, so sorry about that, but I will. So I need a number between 0 and 1. And so I'm going to put in a 0 here and a 1 there just to make my life a little easier as I'm doing this. I want to keep making it smaller till it gets spread out. And now what I notice is I'm clear down here to 0.08, and I'm not that close to getting to where I need to be, and so I actually might want to go back in here and make this 0.1. And the only reason is it just makes it a little easier to do the sliding. And so I slide it down, and now as I look at it, that looks pretty good, right? That's pretty similar. Now what I'll do is use C to slide it back or forth, so I can come this way with it, right, and move it that way, or I can go this way with it. But you see, no matter which one, I can't make it. So in this case, and I can decide, do I want to slide it forward or backward? Doesn't really matter. And here, I need a number way bigger than 10, and I can get an idea of what I need. So for instance, I can start at 0, and heck, I'll go clear to 100 here. Hit enter. Now I can get some idea of what I need simply by doing this. Set it at 0. Look at the top here, and that's a little less than 100. Look at the top here, and that's like 175. And so I need to get up here at like 90 or so. So I get to there, and that is looking mighty good. So 82. And as you look at this, I'm going to put this on projector mode. Sorry about that. Let you see everything a little better. So I've gotten these numbers simply by sliding these around and knowing what I needed to do. I had my little bit of a brain fart there for a minute with the B, but again, that's the nice thing about technology is I can misspeak, make a mistake, but the technology sort of instantly showed me that I was making a mistake, and I could fix that. Okay, so with these periodic functions like sine and cosine, doing this is pretty easy. Now there's a bit of philosophy here. Now notice, it doesn't fit the data so well down in here nor up in here. Up here, it's a little bendier. The data aren't quite as bendy. I know I'm getting technical, but they aren't quite as bendy as the actual sine function. Now, there are some more complex things one could do to try to straighten that out on the inside as you went along, but there you get into the philosophy. Is the question, what is it? Is it that we are trying to exactly match the data, or is it that we're trying to show the basic structure of the data and what's going on? And so if the model's purpose is to give insight as to what's happening, well, I would say this is a great model in that it fits the data pretty closely. There are definitely some gaps in there, but it fits it pretty closely, and I would definitely say, yep, you're pretty much following a sine curve. And so if I wanted to go do some other modeling where I wanted to use sunlight, probably the sine function with A is 0.29, B is 0.0174, C is 82, and D is 0.518. That would work pretty well, I think. And so we can get that and say, oh yeah, if, for instance, if I'm writing a video game and I want, somehow this video game includes sunlight or sunrise and sunset, and over the course of a calendar, I would feel very comfortable in setting up that video game just using this model, this sine function here, to model the sunrise to sunset. Not a problem. I'd feel very good about that. And now on the other hand, if you have to get it more or less in your mind exactly right, and this just won't quite do, oh well, okay, then that's a different choice of model. And in that case, what I might do is actually not use a sine function like this, but use a bunch of quadratic functions or something along those lines, and just fit a little bit at a time. And actually, my choice, what you find in most applications where that is what you're trying to do is get right. You're trying to match a curve exactly. Because you want that curve, you don't really care what's going on, so to speak, is you would use usually piecewise cubic polynomials, and you would just attach them as a piecewise function, and use a cubic kind of in here, and then a new cubic in here, and a new cubic there, and a new cubic there, and you just make sure they all match up. We're not going to look at something like that, certainly not at this point in the course, maybe never in the course, but it can be done. But here, a big part of modeling is just what's going on, because the math gives us that nice thing. What's the period? Well, it is a period of a year. Yeah, makes sense. If it wasn't a year, I would think something was really strange and all my astronomy facts are way off, right? And then, the idea that it looks like it would repeat as a sine function would repeat. And it's symmetric, or pretty symmetric here as we look at this. And, so we see those symmetries, we see that it was steepest here in the middle, and those are all properties of a sine function. So if I'm just trying to understand what sunrise to sunset does over the course of the year, a sine function tells me very, very nicely. Okay, so we'll call that one good, and we'll make a couple more videos fitting some other data.